Hello everyone, and welcome. Today we are going to dive into a fundamental architectural breakthrough for large language models, Attention Residuals, or Attention Res. Based on the technical report by Moonshot AI's Kimi team, we are going to look at why it's time to replace the traditional fixed accumulation in LLMs with dynamic, depth-wise routing. Let's jump in. To understand the motivation, we need to look at what we call the time-depth duality. Think about how recurrent neural networks use to compress an entire sequence of past tokens into a single hidden state, creating a severe bottleneck. The transformer solved this sequence bottleneck by using attention to scan across all past tokens. Today, standard residuals suffer from a nearly identical issue. They compress layer depth into a single hidden state. As the slide points out, we solved the sequence bottleneck with attention, and it is time to solve the depth bottleneck the exact same way. Let's look closer at the problem, specifically PreNorm dilution. Standard residuals use fixed unit weights, creating what you can visualize here as a dilution funnel. Because of this unweighted accumulation, the magnitude of hidden states grows linearly as the network gets deeper. The consequence is severe. Early layer information is statistically buried. Deeper layers are then forced to learn increasingly massive outputs just to have any meaningful influence on the residual stream. The solution is full attention residuals. Instead of depth-wise linear accumulation, we introduce depth-wise softmax attention. At each layer, we introduce a single learned, decoupled pseudo-query vector. This allows the layer to selectively pull exactly what it needs from anywhere in the network's past, rather than relying on a diluted, accumulated mess. Now, there is a catch when we move to massive scale. While full attention res is computationally free in vanilla training because activations are already saved for backpropagation, we hit a scalability wall in distributed setups. Pipeline parallelism and activation recomputation require explicitly saving and communicating all of these outputs across stage boundaries. This creates a massive OLD communication overhead that cripples training throughput. To solve this, we introduce the practical fix, block attention residuals. By grouping the layers into n blocks, empirical proof shows that about 8 blocks is optimal. We reduce the overhead from OLD down to OND. This brilliantly captures almost all the benefits of full attention res while requiring us to store only 8 hidden states per token. Making this work requires serious infrastructure engineering. The first piece is cross-stage caching. In a pipeline setup, sending full history across stages causes redundant data transfers. Instead, we have ranks cache previously received blocks locally, meaning stage transitions only transmit newly completed blocks. This drops the peak per transition communication cost dramatically, enabling full overlap with computation during steady-state training. The second piece of engineering is two-phase inference. In Phase 1, we perform a parallel batched memory read, where all interblock queries execute simultaneously. In Phase 2, interblock partial sums are merged sequentially using online softmax. This reduces inference memory I/O from 34D in prior methods to just 5.5D per layer, keeping the latency overhead at less than 2%. This brings us to mapping the residual landscape. Compared to standard residuals with their static weighting, or highway and multi-stream methods that use dynamic but constrained access, Attention Res completes the puzzle. It accesses all states dynamically, governed entirely by softmax attention routing. Now for the proof points. Number 1, eliminating PreNorm dilution. By using selective aggregation at block boundaries, block attention res resets accumulation. As you can see on the charts, this yields bounded hidden states and perfectly stable gradient flow across extreme depths, entirely fixing the exploding magnitudes seen in the baseline. Proof point 2 is consistent scaling superiority. When evaluated across 5 distinct model scales ranging from 194 million to 119 billion parameters, Attention Res consistently outperforms the baseline. It achieves the exact same loss as a baseline model trained with 25% more compute, effectively giving us a 1.25x compute multiplier. And crucially, the block efficiency curve perfectly hugs the full attention res curve at scale. Proof point 3 highlights our Kimi linear 48B model, pre-trained on 1.4 trillion tokens. Attention res outperforms the baseline across the board. We see massive jumps in complex reasoning, a 7.5-point increase on GPQA Diamond, a 3.6 increase on Minerva Math, and a 3.1 increase on human eval code generation. This strongly suggests that depth-wise dynamic routing selectively unlocks complex, multi-step reasoning. What is the network actually learning? Our diagnostics reveal 3 key behaviors. First, preserved locality. The strongest attention still naturally remains on the immediate predecessor. Second, learned skip connections. Layers dynamically route to distant early layer outputs when specifically needed. Third, layer specialization. Pre-attention layers broadly scan deep into network history, while pre-MLP layers restrict focus purely to local inputs. This has major architectural implications. Under strict flops and parameter constraints, attention res shifts the optimal architecture configuration. Because attention res exploits depth radically more efficiently than standard architectures, the physically optimal LLM structure becomes deeper and narrower. To synthesize our findings, conceptually, depth-wise softmax attention is the inevitable successor to standard residuals. Engineering-wise, through block partitioning and cross-stage caching, it is a highly scalable drop-in replacement. Empirically, it fundamentally shifts optimal model architectures and drives state-of-the-art multi-step reasoning. It completes for depth the exact transition that transformers achieved for sequences. Thank you.